Chapter 18, Part 2 on entropy, enthalpy, and how this relates to reaction spontaneity. So what we can do is take some of the things we talked about in Part 1 with your laws of thermodynamics and apply that to how we can determine whether or not a given reaction is going to be spontaneous or not. So according to the second law, our change in entropy, which is our delta S, must be greater than the heat over temperature, which is your delta H over T. Unless you are at equilibrium, equilibrium would occur during a phase change, which then is going to be equal to. So we can write a relationship between this where your enthalpy must be greater than or at least equal to this delta H over T. So if we rearrange this, we can bring T over. And then if we combine all of our variables onto one side, so we subtract over this T delta S, that means 0 must be greater than this whole quantity for a spontaneous reaction. So for a reaction to be spontaneous, this whole quantity has to be something less than 0 or it has to be negative. If it's positive, then it's non-spontaneous, and the reverse would be spontaneous. And then if it's equal exactly to 0, then we can assume the reaction is at equilibrium. So a physicist named Gibbs introduced this idea of free energy, which actually gave this inequality of value. And so the free energy has this energy G. So for a spontaneous reaction, this is the equation for Gibbs free energy, which is your enthalpy minus your temperature times your entropy. So this allows us to actually have a numerical way to determine whether or not a reaction is spontaneous or not. So changes in enthalpy and entropy result in a change for this free energy. So our delta G, change in energy, is equal to the change in enthalpy minus the temperature of this change times the entropy change. And if delta G is negative, then you can predict that the reaction is going to be spontaneous. If it's positive, it's not spontaneous. And if it's 0, it's at equilibrium. So what we typically measure is something called the standard free energy change. And sometimes it's called Gibbs free energy change, which is the energy change when they're in their standard states, which just means we're at 1 atm and 25 degrees Celsius, about room temperature. So we put a little naught there, that little 0 that's like a Celsius sign, like a degree sign, that represents the fact that we are in standard states when we're doing this change. So we can rewrite that our Gibbs free energy at the standard state is equal to the enthalpy of their standard states, temperature, entropy. So when we look at our units, energy is in a unit of energy, so typically joules or kilojoules. Enthalpy is typically measured in kilojoules. Temperature has to be measured in Kelvin. And entropy is typically measured in joules. So what we have to do is convert all of these energy units into the same unit. So either change them all to joules or either change them to kilojoules. Your temperature just needs to be in Kelvin no matter what. So what's the standard energy change for this reaction? So we have to look up our delta H and delta S values from charts, and we can use the summation law to figure out what the change will be for a given reaction. So our enthalpy values and our entropy values. So let's see, our enthalpy for N2 is 0. This is 218 times 3, because we have 3 of them. And we have negative 45.9 times 2. And then our entropy is 191.5 for N2, 3 times 130.6, and then 192.3 times 2. So I just looked those up from these charts in your book. You can also Google them. There's also, all of these charts are also in the very back of your book as well in one spot. So our enthalpy change for the reaction is going to be our enthalpy of our product total minus the enthalpy of our reactant total. So we want to add up the two values of our products, 218 times 3, and then, our negative 45.9 times 2, minus our, once for our energy of our reactants, and you get negative 309.8. These are all in kilojoules per mole. And the same thing for our entropy, our product total minus our reactant total. These are in joules. I'm going to change them to all the kilojoules. That one's fine. This one, oops, this is, negative 0.1987 kilojoules. That way they're both in the same. So now we can substitute these values into our Gibbs free energy. So we found our enthalpy change was negative 309.8 minus our temperature, which is 298 Kelvin, so negative 250.6 kilojoules. So this is going to be spontaneous as written. From left to right, reactants to products, it's going to be spontaneous because it's a negative number. The other way we can calculate Gibbs free energy total is if you have the Gibbs energy of each individual substance, reactant, and product, and do a summation law, just like we do for the enthalpies and the entropies. So we can do for this reaction, you would have to look up these values. They're in your book. And we want to multiply them. It's negative 394.4. And then 3 times negative 228.6. So you would do the total products, the total reactants, so we would do, this is for the whole reaction, would be the products minus the reactants. These are typically also reported in kilojoules. So we can determine whether or not we think a reaction is going to be spontaneous or not. We can predict it basically just by looking at what signs your enthalpy and entropy are. So there are 4 possible combinations of entropy and enthalpy signs that would give whether or not your Gibbs free energy is positive or negative, which would then help us determine if it's spontaneous or not. So if enthalpy is a positive number and entropy is a negative number, then no matter what your temperature is, your Gibbs free energy is going to be positive, which means that this reaction is always going to be non-spontaneous. If we reverse that, negative enthalpy, positive entropy, Gibbs free energy will always be negative. These will always be spontaneous. If they are both positive, then that will be dependent on what the temperature is. It can be positive or negative depending on if you have a high or low temperature. These will be spontaneous at high T's or high temperatures. Now you can actually calculate what the actual temperature is by high temperature, but it typically means like several hundred into the thousands. If they're both negative, again, depending on the temperature, your delta G, your Gibbs free energy can be positive or negative. these tend to be spontaneous at lower temperatures, so at closer to room temperature, at closer to 0. Whether or not our spontaneity is spontaneous or not, you can also tell based on whether or not your Gibbs energy is a large or small positive or negative number. So if it is a large negative number, then that means most of the reactants have turned into products, which means it's going to be spontaneous as written. If it's a large positive number, that means few reactants turn into products. And it's going to be non-spontaneous as written. If it's a small negative or small positive, so that means from negative 10 kilojoules up to positive 10 kilojoules, then we have an equilibrium mixture of reactants and products. So we don't have one spontaneous or non-spontaneous. We just have an equilibrium mixture of the two things.